Good point. That's actually a good point. Okay. Let's see. I can do it like this then. Okay. So I'll try my best, but it might look a bit awkward sometimes if I do it like this. Okay, then I'll just get started. So, hi guys. Thank you for letting me present here. My name is Lieuwe Bakker. I'm a PhD student in Alexei Fedorov's group in the Russian Quantum Center. Today I will talk to you in real life, which I think it's been a while since I've actually stood in front of a group like this. I will talk to you about time crystals and dissipative coupled bosons. So I'll be presenting some results that we obtained in collaboration with Denis Kurlov, Murat Bahovadinov, Dmitry Klimer, Misha Platyukov, Vladimir Gritsev, and of course my supervisor Alexei Fedorov. So let me just get started with the outline of my talk. So first I will just give you a short introduction of the type of physics that I'm investigating. Argue I think that's interesting, and I believe everybody else agrees with me on that note, but still. Then I will make a connection to time crystals. This is a certain dissipative phase of matter, or not necessarily dissipative, but this is a new phase of matter, which non-equilibrium phase of matter in particular, that currently has obtained some interest in the scientific community. Then I will move on to discuss the model, two-mode bosonic system with a Kerr nonlinearity in it, and show you the results that we obtained and our conclusions that we draw from it. So the type of physics that I'm interested in, actually I got into this field during my master's already, when Vladimir Gritsev introduced me to this concept of driven dissipative systems. These type of systems are not really taught, for the most part, at least in Amsterdam, I can assure you, are not really taught as part of the regular curriculum or anything. So for me, this was entirely new, and at the same time, it's omnipresent, right? Systems which experience some kind of drive and also have some dissipation. We see literally everywhere. So in that sense, they're actually really important. So here I just give two examples of some very obvious driven dissipative systems, for example, STAR, where we have some influx of energy due to thermonuclear reactions, and it can dissipate energy through radiation. And we observe some kind of steady state, like some phase of matter, which is just a normal star. If we vary any of these parameters, for example, we increase the drive by changing the, the type of reactions that we have in the core, then it might undergo some kind of phase transition, and it will become like a red giant or something. I don't know, I'm not an astrophysicist, but something along these lines. So these are non-trivial phases of matter that really only exist, should I stand here? That really only exist because there is some interplay between drive and dissipation. Another example that I've listed here is, of course, life, because, we need energy to sustain ourselves, and at the same time we have to dissipate heat through our skins, for example. If you take one of these two away, then you die. Okay, this is all nice and well, but then what is it what I want to investigate? Well, in order to exemplify this a little bit, I just put equilibrium physics next to non-equilibrium here, and show you exactly. And this is the part I'm interested in the question mark. So right, in equilibrium physics, we know how to describe our phases of matter using equilibrium phases. We have phase transitions using some kind of order parameter. By the way, for simplicity, I'm just considering regular thermodynamic phase transitions, not topological phase transitions, but the story remains the same, roughly. And we have, and actually we know all the phase transitions in equilibrium physics because we have this concept of universality classes. So this is all great, and in non-equilibrium physics, let's move to that point, which I'm interested in. We don't have these thermodynamic phases that we have in equilibrium physics, but we have this steady state phase. For example, the star that I just mentioned. Then if there is some phase transition occurring in this system, this is of course simply a change in the correlation functions that we measure in this steady state solution. But to our knowledge, this part, we don't know everything about it. So it's not known which type of dissipative or like dynamical phases of matter there are. And we surely don't have any idea of universality classes in quantum physics, right? So in classical physics, there is some notion of universality classes in non-equilibrium physics. Yes?
What do you call universality classes?
In like this one?
In equilibrium case.
In equilibrium case. So universality classes is, you know the notion? Is it? Oh, okay. So what it essentially means is that if you look at the correlation functions of a condensed matter system near a phase transition, then the correlation lengths, for example, they diverge, right? And this divergence is governed by some kind of exponent if you look at of this correlation function. And it turns out that many different systems, which like microscopically look different, they have exactly the same behavior when you go through a phase transition. And this is, like specifically, they have the same exponent in that sense, same exponent in the correlation lengths. And you can actually classify these exponents. And well, this really determines everything you need to know at the point of phase transition for.
If the exponent is a continuous variable, so what kind? How do you group different?
They're not continuous actually. So no. So they are certain systems have like their own exponents. So I actually don't know them by heart, but I believe that the Ising model has. I mean, so there's like a whole bunch of exponents. Each related to their own different correlation functions, right? But usually they can be a continuous number, but really what we mean by when we say class is that if we look at two different models microscopically, for example, the Ising model and some other, I don't know, like percolation model, then it turns out that the exponents that they have at the phase transition is the same. Even though they're completely different systems, they have the same phase transition.
So they're exactly the same?
At the point of phase transition, yes. Yeah, and in that sense, they behave completely similar. And that's kind of the point. So we can classify the phase transitions in equilibrium thermodynamic phases according to these critical exponents, they're called. Does that make sense?
Yeah.
Yes? Okay, great. So, and the thing is that in quantum physics, we also have some concepts like that, but in non-equilibrium quantum physics, this is unknown. And there's actually some very nice connections between these universality classes and symmetry structures and everything, but okay. That's...
Now we are talking about the divergence in correlation functions of the steady state of the
Yes, exactly. So we look at steady states, and then if we look at the point of phase transitions, then there is no known concept of universality classes. And also at this point, right, so which non-equilibrium steady states do we have, which different phases of matter in that sense. So I will show you, for example, the dissipative, not dissipative, but time crystals are a type of non-equilibrium phase. Okay, shall I go on, or? Yes, cool, thanks for the question. So yeah, the type of system that I'm interested in, I mean, these non-equilibrium drive and dissipation type systems that can become very complicated. So I'm going to make my life a little bit easier, and I consider only the case when we have Markovian dissipation. So schematically, what it looks like is this. We have our subsystem in orange over here, which is embedded in some kind of bath. So experimentally, what this means is you have your subsystem in orange, which is, for example, some atoms in some cavity with and some photons maybe also. And this cavity is then in your lab, and you're shining lasers at it, and this laser is then the bath, and it might, some photons might leak out of the cavity, and this is then also going into the bath. So that's essentially what it looks like in real life, but schematically like this. And if we have, if we make an assumption on the correlation times of our subsystem and the bath, and the interaction of our subsystem with the bath, like this, we can actually make a Markovian approximation. So, like intuitively, what you have to think of here is that the time scales of our subsystem are very much longer than, for example, the time scales of our bath. So, from the point of view from a system, if something happens in the bath, it happens immediately. And even more importantly, the bath is also very big. So say that I leak some energy out of my subsystem and it goes into the bath, it's gone and it's gone forever, and no one will remember that it was there. And this lack of memory is what allows me, or not me, but what allowed people in the 70s to make this approximation, which is this Markovian approximation. And well, there's some other fine details there, of course, but not really important. It turns out that in this case, it's possible to write down a general form of the master equation, really. And this is called the Linblot equation. So I've written it down over here. So yeah, this Linblot equation is named after Goran Linblot, like a Swedish physicist from the 70s. But my supervisor, Vladimir Gritsev, also always likes to mention that this form of the equation is actually already mentioned in Soviet journals in the 50s or something. So I think that's a pretty funny, funny piece of knowledge. But all right, not important. So let's have a look at this equation just to know what we're dealing with. So we have, we're looking at the subsystem, right? So this is the density matrix of a subsystem only. This is the time evolution, and it's generated by the Liouvillean, which is defined as follows. So we have a unitary part over here. This unitary part is simply the Liouville von Neumann equation type, and it just governs the internal dynamics of our subsystem. And this is nice and unitary. This is nice and unitary and all the good things, really. And then we have these terms over here, and these are called the dissipators, where these operators AJ are called the jump operators. And they really determine the way in which your subsystem can interact with the environment. For example, the way in which it can decay. It can release photons into the environment, for example. And of course, there is some interaction strength gamma over there. So this is what it looks like. And I mean, some people like to do computational physics, so for that convenience, this is the factorized form of the equation. But it's really just factorization of matrices. So, okay. So maybe let's look into a bit further on what the spectrum of a typical Liouvillean looks like. So here's an example of a picture that, like, a generic picture that you can see. So first off, notice that the eigenvalues of this Liouvillean can actually be like imaginary numbers, right? They can be complex. This is because we don't just have this unitary part in our time evolution with the Liouville von Neumann, but we also have this dissipator. So yeah, well, and this is not unitary, so therefore we can have these imaginary eigenvalues. Also note that all the eigenvalues are lying in the left half plane. This is because in this, in the way that where we put the i's essentially determines that the real part determines how fast the system decays, right? Because dissipative systems tend to decay, and if this was positive, then your system would blow up, right? So essentially, in order to preserve the trace of our density matrix, it has to be negative. Furthermore, whenever you have like an finite imaginary component, then there must also be a complex, like a conjugate to it. This is because the density matrix is Hermitian, so the density matrix is Hermitian. Okay, so these are just some details. Now, the interesting parts. So every dissipative system, which is described by this Linblot equation, or Liouvillean, has this, like this zero eigenvalue, which is associated to the non-equilibrium steady state. This is essentially the state, like intuitively, this is the state to which the system will relax over infinite time, right? For example, in the example of the star, you know, like it starts up, right? Maybe in some weird explosion or whatever. You let it go for a while, and at some point it gets into the steady state where nothing happens anymore.
It's exactly zero, right?
Yeah, it's exactly zero. Yeah. Right. So it's because the time evolution will be e to the 0 times the density matrix, and then you get 1 times the density matrix. So at infinite time, you want that the system no longer evolves. Essentially, that's kind of like the idea. Mathematically, it's a consequence of Brouwer's fixed point theorem for these complex trace-preserving, completely positive maths.
Why call it non-equilibrium? Because if you have some external graph, for example, constant graph, but Actually, if you have some change in this drive, which drives the system out of this steady state, then it comes again into the steady state probably if the drive is again restored or somehow. What's not the equilibrium steady state?
The non-equilibrium part is really just referring to the fact that we have dissipation in this channel. But I mean, for me, it's fine if you also call it a steady state.
Yeah, but it's like equilibrium between the drive and dissipation. Yeah.
Sorry, could you repeat the last part?
I mean, this is what we have in steady state. It's kind of equilibrium between the drive and dissipation.
Yeah.
The system takes energy from the drive and
right.
dissipates into some modes.
Right. But this non-equilibrium is really just focusing on the fact that we don't look at isolated systems. So that's really why. But okay, it's fine. I mean, you can take out the N and the E, and it's good. We're talking about the same thing here, regardless, I believe. So. Yeah, then we, aside from this non-equilibrium steady states, we have these decay modes over there, called decay modes because they will decay if you let them long enough, and the time scales which it will take for the system to decay to the non-equilibrium steady state is governed by this delta over here. This is called the dissipative gap. This delta actually plays the same role in this dissipative quantum mechanics as the regular gap between the ground state and the first excited state plays in regular unitary theories. So that means that if this disappears, we expect that there may be some phase transitioning happening, right? For example, so this mode might move towards this non-equilibrium steady state, and then you just end up with some thermal state. This is usually what happens to these dissipative systems. And then if you change the parameters even more, you know, like then maybe the gap reopens again, but now we have different correlation functions, right? And then we have had a phase transition. And what's going to be interesting for us is also the notion of these oscillating coherences, because it's not, these might also exist, actually, and the thing is that these do not decay, right? So it could be that, for example, this dissipative gap, it closes in on the imaginary axis, and you actually end up with a non-equilibrium steady state and several coherences here above and below, and then that means that your like final infinite time state, right, that you observe after a long time, is going to be some oscillating state. So there's some oscillation in it, and this will not decay, it will persist.
Wait, but if you apply the Liouvillean many times, you will always end up in the non-equilibrium steady state with zero eigenvalue, right?
Well, so that's what I'm trying to say, so not necessarily. It could also be that maybe in some thermodynamic limit, you also observe these coherences.
What defines where you go?
Sorry?
What defines to which point you get?
I guess that depends on the theory, I think. So I will show you an example of our like in our like model where this happens. But before I do that, I just want to like discuss with you this notion of this oscillation in this steady state solution, if you will. It's not really a steady state; it's like an oscillating steady state, because this is like an interesting new dynamical phase of matter. And the community nowadays likes to call these time crystals, so I think it could be useful to first discuss that a little bit and then move on to our actual system. Yes, so time crystals, what are they? Well, I already just mentioned it essentially, but let me just repeat it just to be clear. A time crystal is a system in which there is some periodicity in time in its like steady state solution. No, yes, you're going way faster than I am. So yeah, Rabi oscillations exactly are not time crystals. Yeah, sorry. Oh, you're going way faster. Maybe, okay, then I'll go a bit faster then, because you guys are already at the point where I wanted to go to. But yeah, so time crystals, there is some kind of periodicity in time for the system. And this is not a very strange observation, right? Because you already mentioned many systems, for example, a singular qubit also has oscillations associated to it. So this is not very strange, but nevertheless, it's also a bit awkward because we want to be careful what we talk about here. Because if we say that there is some kind of motion in its like a steady state solution, right? Because there's some periodicity, this implies there's some motion. This comes like perilously close to like perpetual motion machines. So you kind of want to be careful about this, right? Classically, of course, this is impossible because we have the second law of thermodynamics. But when it was introduced in 2012 by Frank Wilczek, this concept of time crystals, he also mentioned, for example, superconductors. In quantum mechanics, we have this example where we have a current and it can just remain indefinitely in the system. So this is the steady state solution, if you will, but definitely something is moving. So is it really that weird that maybe in quantum mechanics something like a time crystal could exist? Of course, superconductors are not time crystals, but yeah, like that. It's just an argumentation that he had. I thought it was a fair point. So very quickly after he proposed the existence of these so-called quantum time crystals, other groups also made suggestions. For example, this is a group that proposed to put atoms on a ring, and we have some like time-independent homogeneous magnetic field blasting it, and then they predicted that they would observe this following periodic nature in the correlation functions of this system. So this sounds pretty cool, but it was actually wrong. It's impossible, turns out. In particular, these type of systems cannot actually have a time crystalline phase. Do you have a question? Oh, sorry. This was a result of a paper published by Haruki Watanabe and Masagi Yoshikawa from 2015, which ominously is called Absence of Quantum Time Crystals. And they proved actually that the type of systems proposed up here cannot exist. And let me just be very clear here. What they actually proved is that it's impossible for a system that has a continuous time translation symmetry to break to a discrete subgroup. This is impossible. The way they proved this is actually quite simple. So they used some, personally, I think it was some remarkably simple arguments and some mathematical theorems that just proved this straight away. But the intuition behind this is actually also very simple. If you solve a wave function based off operators that have continuous time translation symmetry or are time independent, for example, just consider time independent Hamiltonian, then by construction, your states, your expectation value should not be time dependent. So that was kind of the reason, that's kind of the reasoning that they have. But luckily our story doesn't end here because otherwise I could quit now and say goodbye. But exactly what is possible, it's still possible for a discrete to discrete time translation symmetry breaking. So it is possible for a system to undergo which already has this broken symmetry, to go to another, translation symmetry. And an example of this is, for example, Floquet-driven systems. So these are systems that are driven using some periodic drive. So, of course, it's kind of, you can already imagine that it would not be strange to imagine that this system essentially follows this drive along. So there is some motion in this system, but perhaps it could be that if you change the parameters of a system in such a way, then suddenly we find a subharmonic response, right? So we find that the system starts to oscillate at a frequency which is different than the frequency with which you drive it. And this is now what we call discrete time crystal. So this has been established roughly. So an important thing that we want to see is a response at a subharmonic frequency. But that does not tell us everything because, and you already mentioned this, Rabi oscillations are not time crystals. And actually there's many systems that exhibit this subharmonic response. But that does not make them time crystals because there are some other things that we actually want to keep in our minds. For example, a very important aspect that I believe everybody agrees with me, time crystals must have many-body interactions. This is a must-have. Because otherwise you can say individual atoms, time crystal, no. For also we want long-range order. And this is actually in the same idea, but we want that the whole system as a whole has this time crystalline structure, not just a singular small piece inside this system. Right, a single Rabi oscillation in the chain of atoms is still not a time crystal. And then finally we have this concept of crypto equilibrium. It's a bit harder to describe, but what it means is that we don't want that our system generates entropy. And more intuitively, you can describe it as there must be some kind of reference frame with which you can move along with the system such that it looks as if it's static. So in here they give some examples of systems that do have this subharmonic frequency response, but do not actually are time crystals. For example, the AC Josephson effect is not a time crystal. It might have many body interactions, but it does not have long-range order, for example.
Can I just myself summarize? So, time crystals are crystals that have long-range order in space, and at the same time they're supposed to have long-range order in time.
Yes, exactly. Actually, it was also in this. So here you can actually see it, right? So it's x1 and x2, so it's order in space and in time, crystalline space and time. Yes. So good question. Yeah, absolutely. So this table I took from a paper published by these guys in 2018.
You can also clarify with what's
Sorry. Oh, what it was. Oh, okay. So let me maybe go to an example. But actually, so it turns out this one is a bit hard to work with usually. But let me just go to an example then, because you might ask, what is a good system then? And there is actually one class of systems that readily can present this in a time crystalline phase. And these are, oh, by the way, I'm talking about closed dynamics right now. So at this point, I'm talking about closed dynamics. And I will go back to open dynamics in a second. So if this is an example of a Floquet-driven system, where we have one drive period is made up out of this H1, H2, and H3, which are of this form. And schematically, it looks like this, right? So we have a spin chain over here, and we just flip them all using this H1. Then we let them interact with each other, and then we introduce some disorder and rinse repeat. Yes? So what they observed then was this picture. What you see here is on the y-axis you see the magnetization in the x direction, for example. And the colors indicate the different ions in the chain that they investigated. And this is the Fourier Fourier analysis of this oscillation, and you see like a peak at half the frequency. This is subharmonic response. And then, okay, so we have subharmonic response. This is good. Then there were three other things. We needed to have many body interactions. Well, we have that, H2. And we needed to have long-range order. And we have that too. If you look at this point, you see that like all the colors are all pointing in the same direction. So there is long-range order in the system, right? All the spins are pointing roughly in the same direction in X. And finally, we needed crypto equilibrium. And this is also existent because what we can do is you can actually move along with the magnetization of these spins, right? So the spins are essentially flipping between, like if this is the X direction, right? So they're going from this to this, to this, to this. So you can simply move along. And if you do that, then it looks like the system is actually standing still. So this is the crypto equilibrium. And this is a time crystal, right? So this is experimentally observed. Cool?
So this reference frame must exist. There should be
yes, at least in this conserved dynamics, absolutely. But in practice, it's pretty hard to work with this because experimentally you always get this. Yeah. So there's always a little bit. So this crypto equilibrium point is actually a bit hard to work with. But yeah, like.
But if there was no dissipation, then it would be.
Yeah, in an ideal world, yeah, then it would work. Yeah, in this case, it's. Sorry.
What you show is the experimental data, right?
Yes. I forgot to put the source here.
Probably these points correspond to some measurements, and these oscillations, my guess is what they edit is.
So these points are magnetization that they measured of individual ions in a chain that are like.
So they have chain, and in your model there is a kind of interaction, a long interaction.
Yes.
Between this spin, for example, this spin, right?
Yes.
But how to realize this experimentally? Experimentally, we can make a chain.
That's a good question. Although I must admit, I think this could have been done using ions. I think this was done with ions.
Okay, they're not random ions, but this is kind of chain in which trapped ions, in which you can make some control of states and transfer the states from one to
Yes, to give you gates with every pair you can do with ions.
through the neighboring ones.
Through the common oscillation
Great. Yeah, I was hoping that somebody here who knows a bit about experiments can answer that question for me, because yes, I don't know about experiments. I should have, I now realize that I forgot to put the source here, my apologies, so I will do that later. Okay, so this is all for isolated systems, but maybe let's move on to dissipative systems, because that's actually the thing that I cared about, and this brings us back to these, right, these oscillating coherences that we noticed. So in dissipative systems, time crystals can also exist, actually. There's no reason to, like there's no no-go theorem or anything. And actually, so this is just to remind you, right, we have these coherences, and this might be oscillations that might be interesting. And actually, this group from University of Hamburg, Kessler et al., they experimentally also claim to have observed a time crystal. And this is a system where they had some rubidium atoms closed in an optical trap, which they would then drive using amplitude epsilon and frequency omega. And then in the upper picture here, you can actually see the driving protocol. So from this line on, you see that they have a certain, right, they drive the system. Well, they drive the system, and then they do some measurements in the response of, for example, the intracavity photons. So this is take some observable, which they then measure, and if you look at the amount of, you can see like there's 1, 2, 3 peaks here, and in the red curve there's only 1, 2 peaks. So there is a subharmonic response in this system. So and they claim that this is then a time crystal. So this is good news for me, because I was looking at the dissipative system, so perhaps there is also a time crystalline-like structure present. So let's move on to my system, or not my system, but the system that we have investigated. It's not mine. So the system that we investigated is one where we have 2 bosonic modes, which are captured in a, what is it called, optical cavity, right, for example. These modes have some interaction parameter u, so for example, we have the blue modes and the green modes. We have some Kerr interaction for the blue mode, and the blue and the green mode are, they see each other through G. There is dissipation, and we have some coherent drive. So this is what the Hamiltonian looks like, right? So we have the regular eigenfrequencies of the A and B modes. We have this parameter G, which connects the two. We have drive, and we have Kerr. And then, of course, the full time evolution is given by this this Lewis-William, which I've written over here, where we also include these dissipation channels. Pictorially, they look like this, right? Okay, so how to attack a system like this and see if there may be some interesting things going on here. So there is a Kerr interaction term, and this is basically impossible to solve. If it's just a Kerr term, it's actually possible to solve for the steady state in this case, which was done by Drummond and Walls in the 70s. But yeah, we have this interaction with another mode, so unfortunately that doesn't work. But we can do a mean field approach. And if we do that, then the time evolution of a system is given by an equation. You can model it in this form, where the matrix A is simply a combination of all the system parameters, and this vector psi is made up out of this y and z, which are related to the particle number NA and NB. So this is just some algebra.
What do you think? Both your oscillators are, or no? Only one oscillator is.
Yeah, so only the B mode has a Kerr oscillator in this case.
Yeah, okay.
And the A mode doesn't.
So the A mode is Gaussian.
The A mode is Gaussian, yeah. So then the mean field approximation is actually pretty good. But yeah, okay. It's a bit trivial, I guess. So really what it just say is just, this gives us some kind of idea of to look at. All right, so this just tells us about the time evolution of the number of particles A and the number of particles B in the cavity. So let's have a look at the semiclassical results. So I just put these over here for you to remember in case you would like. But we're only going to focus on the particle numbers B, actually. Yeah. So this is the full story that we get from the semiclassical approach. So what we're looking at here on the in this picture is we see on the y-axis the particle number squared, and on the x-axis we see, let me try this, amplituda vozdejstwia. Is that good? Vozdejstwia? Yes? Okay, thanks. Yeah. So, the translation was provided to me by Denis Kurlov, my supervisor. So what we see here in this red line, this is the steady state solution of this semi-classical equations of motion. So essentially we just put this psi dot to 0 and we solve for the system. And then you get this S-shaped curve over here. And this is pretty common. It's actually called optical bistability. So this is something that's been known for a while already. But we can go a bit further, of course, because we have a much more complex system. So we look at the stability of our system, and we find that this branch in the middle of the upper and lower branch is unstable. That means that the system will never relax to this value. But also we found that there's this region over here, which is unstable, in between these points H1 and H2. Points H1 and H2 are Hopf bifurcations in mathematical terms. So this is a subcritical Hopf bifurcation, this is a supercritical Hopf bifurcation. And maybe in order to make sense of what's happening in this picture, it's nice to just start at the small value of, like for example, a value of 1. Like so we start around this point, and then we say, okay, I'm give my system some initial state and let it evolve for some time, and then it will find its steady state solution on the red curve. And then I increase my epsilon, like my drive amplitude, and then I let it evolve again, and like that I can actually move along this curve, and I can reach this point over here. Now what happens now is this is an unstable solution, so it will actually, the system will start to follow these limit cycles that appear from here. So these are actually, so this curve over here, this dashed curve, it indicates limit cycles, and particularly it indicates between which absolute values the limit cycle oscillates. So that looks like this, right? We have a limit cycle in the z-plane, and we actually have two limit cycles here, because we have an unstable limit cycle, which is denoted by the dash curve, and we have a stable limit cycle. So of course, if you let the system evolve indefinitely, it will find the stable limit cycle solution rather than the unstable one, but no, just to give a complete picture. And actually, if you then follow these limit cycles, you find out that at this point here, we have a limit point cycle, and we move into this region of, well, stable limit cycles, right? So that's the solid curve in this picture. Okay. It's hard to do this with a trackpad. So, so then we move on, and at this point, at some point, we reach this period doubling over here. And what that means is it means that we actually, like this limit cycle splits into two limit cycles, or not really splits into two limit cycles, but rather just we get a period doubling. And this can be made explicit if you just look at the Fourier, like the Fourier spectrum of the system. And if we increase even further, then we get another period doubling point, so PD1 in this picture, where actually it's rather a period halving, but all right. So like the two limit cycles coalesce into a singular one, and then they will slowly converge onto this point H2, and then the story is done. So now why is this interesting, this story? It's that even at the semi-classical level, we observe that there is a whole lot of things going on, actually. It's really not a non-trivial, you want to say, hysteresis of different phases that we observe, right? Where we have simply a steady-state solution, then we have these oscillating limit cycles, period doubled state, and regular limit cycles again, and then we move back on to a regular steady-state solution. Now, of course, this is a semi-classical approach, so we would really like to know what actually is going on in the quantum case. But are there any questions about this picture so far?
Well, could you please one more time define the LPC point?
How you find it?
LPC point? LPC, what does it mean?
It's like the limit cycle essentially, where the it's like a point in the limit cycle structures where the unstable limit cycle meets the stable one, and they annihilate, if you want, or okay.
I assume that, I don't know, that at this point the system just switches from the unstable one to the stable one.
Yeah, so maybe just to illustrate what happens. So say that I start out my system in this, where my laser dot is right now, right? So I just started out there, roughly. What happens is it will it will actually find this steady state solution over here, which is the limit cycle. So it will actually just fall into this limit cycle, and it will just start to go around like this, right? So it will never actually find this unstable one, but it is there. It is there. So mathematically, it also has to be there. Does that answer your question? But then, of course, if I start out at this point, I will not fall, maybe not, like maybe I will fall to this point, or maybe I will fall to the steady state solution. That's kind of what this picture tells me. So there's like there's different solutions available to the system depending on where you start out.
You were making a numerical experiment, a lot of numerical experiments.
Sorry, could you?
How these pictures were, I don't know.
How I made them?
How were you made? Yeah.
Oh, well, I mean.
You were starting a lot of, like, I don't know, numerical experiments that were starting from the not so big motives. Like,
I guess that one is from some kind of eigenvalue calculation, right?
So
The A panel. The panel A.
the panel A. So what you do here? Okay, the way I made it is, first of all, there is a very let me. So the red curve is simply made by putting psi dot equal to 0 and then solve for the different solutions. Then, if you want to look at the stability of this solution, you actually have to. You can make this is basically stability. Sorry.
linearize this part.
Yeah. You can linearize it. You can add these, like you can make an assumption on the exponents, and you will find that some might be positive or negative, whatever, or imaginary. Absolutely. Sorry. And then you can identify which regions here are unstable. These limit cycles you can then find by simply probing the system numerically. All right. This is what you can do. But
How does that happen? What are the details?
oh, the detail. Okay, sure. Yeah. So what I do, for example, is say that I start out from, I know exactly the point which corresponds to this point on the line over here. Right? So then I can simply move my epsilon 1 a bit. So I can just take some initial state ansatz, and I can decrease my epsilon 1 and in this region, using my initial state ansatz that I had from the previous point. Let the system evolve, right? Just integrate from time 0 to, I don't know, like 10,000. And then you will find like this limit cycle. Because you'll actually you can plot it and you will see that it will converge onto this limit cycle. You will have a stable one. The unstable one is a bit harder, right? So in order to solve it, so there's a very nice package available in MATLAB, for example. You can just use it, which has this pre-programmed. But in order to find this, what you actually have to do is you have to rewrite your, because you can actually also, so this is how you can probe it manually, but you can also probe it by solving this set of differential equations. MatCont. How about, I think you have my phone number, and then I can tell you exactly what I did. MATLAB. Yeah. But essentially what you can do is you can just rewrite this problem into a set of coupled differential or integral equations, which have periodic, you impose periodicity boundary conditions on it, and then it's possible to find also these unstable solutions. So then you're not dependent on simply numerically integrating, because as you say, you will never find them like that. That was a big problem for me. Yeah. So yeah, I ran into this exact problem. But luckily, this whole idea of Hopfifications has been studied mathematically already for like 50 years or something. So it's actually pretty well developed. So I can give you some sources if you want. So I'm counting on you, Victoria. Okay, so let me move on to the quantum counterpart. So in order to do this, we need to first define a thermodynamic limit, right? Because our system, I think I'm going grossly over time, by the way, so my apologies. Okay, that's normal. There's more questions than I was expecting, actually. So okay. Well, as long as you guys are enjoying yourself, and I'm very happy. So let's move on to the quantum results, right? So first we need to define a thermodynamic limit. That's because our Hamiltonian is actually like a zero-dimensional Hamiltonian, if you want. So we need to define a thermodynamic limit. And the way to do this is by, there's actually a trick, it's called the weak interaction limit, the weak interaction thermodynamic limit. And what you can do is you can take the Hamiltonian, or rather the full Liouvillean, right? You can Fourier transform it and map it to a system of Bose-Hubbard Hamiltonian with n cavities. And then this you can map it to it, right? So it's essentially the same, and this number n, the amount of cavities, is then the particle number in your system. The details are a bit boring, but what we have to do is actually rather simple. We just make this identification. So we just identify, we have to plug in this parameter n in these three system parameters. Right, so just to remind you, this was a driving amplitude, or driving in general. This was the Kerr interaction strength, and this is the two-mode dissipation for the B mode. And this is called weak interaction because, well, right, as n goes to infinity, the interaction goes to 0. So if we do this, then we can just numerically diagonalize this our Liouvillean. This is, of course, a bit hard because, well, if you want to do ED, the only way I know how to do this, at least, is to make a Fock representation of your creation and annihilation operators, and then just write down the Liouvillean in factorized form, and then diagonalize. But the problem is that, of course, this is terrible scaling on this, because we have two modes, so we already get like square of the amount, in the cutoff in our Fock representation, we already get it squared, but you also have to vectorize, so it becomes to the power 4. And like the max that we could do, like we had resources to just go up to like matrix sizes of about 1 million and about 1 terabyte RAM, and that means that the maximum Fock dimension that we had was 32 per mode.
But you can diagonalize matrices of size million by million.
Yeah, well, not fully, like sparse matrices, but actually, so there's even more problems here, right? Numerically speaking, because this is not a Hermitian operator. So you cannot use you have to, right, the Liouvillean is not Hermitian. So there are some packages which require Hermitian which are faster than regular ones. So this is a problem, and so basically as soon as you go dissipative, things get hard again, unfortunately. But nevertheless, we can do a good try, right? So let me just show the results. So this is like a generalized picture just as before. And now what we're looking at on the y-axis, here I go again. So dissipativnaya shell. I think this over here is very hard. Yeah. I'm sorry. I try, but this one I just cannot. I just don't. And again, on the x-axis we have this driving amplitude. So dissipative gap versus driving amplitude. And why am I looking at this? Because, well, when this gap closes, it gives me an indication that the phase transition might happen. So if we look again at our story, we see that at the small driving amplitudes, just like in the previous picture, nothing happens, right? We just have our steady state solution, so the gap remains open. And then as we increase the driving amplitude, then we get into this region where we observed all these limit cycles in the semi-classical regime. So maybe something happens quantum mechanically, and, well, it seems like it does. So, for example, we can look at the 0.1, 0.3 here. Sorry, this is like 0.5, right? So as we increase the particle number, so these the different colors correspond to different particle numbers. As we increase it, you see that the gap remains closed. So this is the spectrum that we find. Nothing special happens. But then as we go to, for example, driving amplitude of 1.3, we see that the gap definitely tends to close as we go into the thermodynamic limit. And it closes in two ways. So it closes by this mode over here that wants to fall down on this non-equilibrium steady state if you want. And we have these two modes up here that also, as we increase n, want to move down towards the imaginary axis. And this then are the oscillating coherences, right? Or if we could go further, those could be the oscillating coherences. But we found more in the semi-classical approach. We also found these period doubled modes, so that was around 1.6. So actually, if we look over there, we see the same thing, but now there is a different behavior actually in the way the gap closes. So we see again these two modes over here, which are, well, they correspond likely to this, right? But we also have this other mode at a frequency which is about half of the other of the big ones, essentially, of the big modes over here, that also appear and also want to close down on the axis. But also, this is the point where we start to reach our capabilities numerically, because it turns out that these modes over here are just super elusive. Like they're very hard to compute. So.
This you have for two modes, one is linear and one is non-linear.
So I mean, I've seen also papers where they looked at systems where you have two nonlinear modes, but then there's also again some simplifications that you can make because there's actually a symmetry in your system, right? Because there's a Z2 symmetry present. So this then makes things simpler again, but nevertheless, they did not observe behavior like this. So this period doubling that we see both in the semi-classical and in the quantum regime is something that that to my knowledge is new. Right?
There are no something like many binding interactions or long range order. They all have a certain number of degrees of freedom. So I mean, this is it the same physics which we have in time crystals?
That's a good question. So the short answer is I don't really know. It definitely reminds us of a time crystalline structure. It has a subharmonic response, and we also have many body interactions to our knowledge. And I think that long range, well, I mean, it's a zero-dimensional system, so it's a bit hard to argue whether or not it has a long-range system. But yeah, so this crypto equilibrium, for example, this actually I don't know, right? And also, but the thing is that when I investigated this also in the other papers, this actually never gets discussed at all. So in that regard, maybe I should mention that people nowadays like to call these type of systems time crystals, but it's not necessarily something super new or something in that sense. I mean, you know, period doubling has been, or subharmonic responses have been known for ages already. It's just that we want to try and classify these type of systems, right? That's kind of like the goal. Does that answer your question, sort of? Okay. So maybe like a final picture, or almost final picture, that I want to show you is just to like where we put everything together, right? So we have the ED results and we have the semi-classical results. I'm not going to try to read this. So, and what you can see here is that the periods of both the semi-classical predictions and the quantum predictions actually are pretty close to each other. And then maybe I should also mention that the original driving amplitude is driving frequency here is 2. So we have a response at well 1.5, but we drive it at 2. So we also actually have a subharmonic response in this sense. So this really sums it up. Of course, we can try to do a little bit better, right? Because ED is not the only method available to us. And what we can also do is Monte Carlo trajectory approximations. So I've done that also. So this is well, I haven't really pimped this picture very nicely, I admit, but this is what we see here is we see for n equals 25, we see the behavior of like the oscillations. And indeed, if we take the Fourier spectrum of this, we find that the period is exactly the period that we find over here in this line. And like this, we can increase or decrease our values for n a bit more. So, and it seems that indeed, as we increase n, the oscillations will remain stable longer and longer, which is what we expect, right? Because the gap closes. So, and if we go to infinite particle limit, then it should get infinitely close to the imaginary axis, and these oscillations should persist for long times. Right? So yeah, what are the conclusions that we can draw from all this? Well, time crystals are, well, arguably they are a pretty interesting, like non-equilibrium concept of phase transitions, right? So concept of non-equilibrium phase transitions. It's pretty interesting in that regard. Has many like possible applications, right? So especially in quantum information solutions, it could be very useful. So of course, then the question remains like, okay, in these Floquet-driven systems we have it, but we would like to also see, do these systems also exist in dissipative systems? And what are the classification, like how do we properly classify them fully? Like what do we call it dissipative time crystal? And in our system, we did find like a series, like some really non-trivial dynamics, where you find a series of like driven dissipative phase transitions, because that is clear. We do see several different phases, and these look like they are time crystalline in nature, but unfortunately, like our numerical limitations are limited, right? So, like, it would be nice if we could study it maybe in like experimentally or something. That would be great. Yeah, and that really, I believe that's everything I wanted to say. So, yeah, thank you for your attention, and if you have any more questions, I would like to try to answer them. But yeah, thank you.